Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 4, Topic 1. Navigating Thermal Resistance in Semiconductor Packaging. Understanding Concepts, Significance, and Optimization Strategies. Introduction. Thermal resistance is a critical parameter in semiconductor packaging, playing a pivotal role in determining the efficiency of heat transfer and ultimately influencing the reliability and performance of electronic devices. As electronic components continue to shrink in size and increase in power density, managing thermal resistance becomes increasingly challenging. This overview delves into the concept of thermal resistance in semiconductor packaging, discussing its significance, underlying mechanisms, and optimization strategies. Understanding thermal resistance. Thermal resistance quantifies the opposition offered by a material or structure to the flow of heat and is analogous to electrical resistance. It represents the temperature difference per unit of heat flux, indicating how effectively a material or structure conducts heat. Thermal resistance is typically expressed in units of degrees Celsius per watt, degree C, W, and is a fundamental parameter in thermal analysis and design of semiconductor packages. Types of thermal resistance. Thermal resistance in semiconductor packaging can be categorized into several types, each representing different aspects of heat transfer. 1. Conduction resistance. Conduction resistance arises from the resistance to heat flow through a solid material. It depends on the thermal conductivity of the material and the thickness of the medium through which heat is conducted. Conduction resistance is particularly relevant in materials such as package substrates, die-attach materials, and interconnects. 2. Convection resistance. Convection resistance arises from the resistance to heat transfer between a solid surface and a fluid medium, liquid or gas, through convection. It depends on factors such as fluid velocity, fluid properties, and surface geometry. Convection resistance is significant in applications where forced or natural convection is employed for heat dissipation. 3. Interface resistance. Interface resistance arises from the resistance to heat transfer across interfaces between different materials, such as between a semiconductor die and a heat sink or between thermal interface materials, TIMs. Interface resistance is influenced by factors such as surface roughness, contact pressure, and the properties of the interface materials. Significance of thermal resistance. Thermal resistance plays a crucial role in semiconductor packaging, influencing various aspects of device reliability and performance. 1. Temperature management. High thermal resistance can lead to elevated operating temperatures within semiconductor packages, potentially causing device degradation, reduced lifespan, and performance degradation. Managing thermal resistance is essential for maintaining device temperatures within safe operating limits and ensuring long-term reliability. 2. Power dissipation. Thermal resistance directly affects the efficiency of heat dissipation from semiconductor devices. Higher thermal resistance results in increased temperature gradients and reduced heat dissipation capabilities, limiting the maximum power that can be safely dissipated by the device. 3. Thermal cycling reliability. Thermal resistance impacts the mechanical stresses experienced by semiconductor packages during thermal cycling, resulting from temperature variations during device operation. Higher thermal resistance can lead to increased thermal expansion mismatches and mechanical stresses, potentially compromising package reliability over time. Optimization strategies for thermal resistance. Optimizing thermal resistance in semiconductor packaging involves various strategies aimed at minimizing resistance and maximizing heat transfer efficiency. 1. Material selection. Choosing materials with higher thermal conductivity, such as copper, aluminum, and certain ceramics, can reduce conduction resistance and enhance heat transfer capabilities. Additionally, selecting materials with appropriate properties for interfaces, such as TIMs with high thermal conductivity and low interface resistance, can minimize interface resistance. 2. Package design optimization. Optimizing package design, including layout, geometry, and architecture, is crucial for minimizing thermal resistance and maximizing heat dissipation. Strategies such as increasing surface area, reducing material thicknesses, and enhancing airflow can improve thermal performance and reduce convection resistance. 3. Thermal interface enhancement. Improving thermal interfaces between semiconductor components and heat sinks can reduce interface resistance and enhance heat transfer efficiency. Using techniques such as surface roughening, applying thermal interface materials, TIMs, and optimizing contact pressure can improve thermal contact and minimize interface resistance. 4. Advanced cooling solutions. Implementing advanced cooling solutions, such as microfluidic cooling, thermoelectric cooling, and phase change materials, can enhance heat dissipation capabilities and reduce thermal resistance in semiconductor packaging. These techniques offer higher cooling capacities and can effectively mitigate temperature rise and thermal resistance. Conclusion. In conclusion, thermal resistance is a critical parameter in semiconductor packaging, influencing device reliability, performance, and thermal management capabilities. Understanding the types, significance, and optimization strategies of thermal resistance is essential for designing efficient and reliable electronic devices. By minimizing thermal resistance and maximizing heat transfer efficiency, engineers can enhance thermal performance and ensure the long-term reliability of semiconductor packages in diverse applications. Thanks for watching. Please like, share, and subscribe.